Hello, hello, hello everyone. This is the first talk, the keynote from Alice. I prefer to leave her the presentation because it's quite famous. Then good talk.
Hey everyone, my name is Ryhl, and today we would be talking about actors. Now, you may already know me from my work on Tokio, where I am one of the core maintainers. You may also know me from my numerous posts on the various forums, or perhaps you have seen my blog. At my work, I work at Google in the Android Rust team, where currently I split my time on Tokio maintenance and on writing a Linux driver in Rust. All right, so the idea with this talk is, of course, we're going to talk about actors, but I find that actors have a lot of interesting connections with ownership. And so my idea is that I will also be talking about how ownership works in Rust and how that connects with actors. And the hope is that some of these ideas are useful even if you're not going to write an actor ever in your life. All right. So, what are actors? Well, for our purposes, actors are background tasks that use channels, message passing channels, to communicate with the rest of the program. There are some other languages, such as Erlang, where they have a bunch of opinions about how error handling should be handled and that kind of stuff too. But for our purposes, this is enough. So, in the context of Rust, when are actors useful? Well, the main place that I find that you should be using actors is I/O resources that you want to have shared access to. And now you may say, I know how to have shared access. I just use an argmutex. But it turns out that for I/O resources in particular, there are some certain use features that you just don't get with a mutex that actors provide you. I have them on the slides, but so for one, you can initiate operations without anybody having to tell you to do so. And this is useful for, say, sending a ping. It is another thing is that even if there is some outside influence that started the operation, then they don't have to stay around until the operation finishes. It can continue independently. So yeah, that's the idea. When I talk about design pattern, I like to give an example that I call a recipe. So in this case, we will be discussing an actor where, well, it has a receiver for a message passing channel, and we have a TCP stream, which is some I/O resource. The idea is that you can write a string to this TCP stream, and we assume that the other end will respond with an integer. So this is a pretty simple example of an I/O resource. And so actors communicate over message passing, so we also define a message type. And so the message type, in this case, we have one kind of command. The command is to send a message, and you have the string. And then we include this thing called a one-shot channel for the response. Now, you might think, what's up with this one-shot channel? And this is a clever trick, because if you want to get responses from your messages, perhaps the first thing you think about is just to put a sender in the actor. this has some challenges with, it can be pretty difficult to connect up which response comes from which message. So using a one-shot channel like this, such that each message has a receiver associated with it, makes it much easier to do this. Okay, so, I mean, our example also needs to actually send these, like handle these messages, send them in a TCP stream. So you do that like this. You have a handle message, you get the message, you match on it to figure out what kind of it. You write the message, you read the response, and you send the response to whoever wants the response. So yeah, it's not too complicated of an idea, I think. So we also need a run function. It looks like this, pretty simple, a while loop. We receive the message, we handle the message. Once the channel is closed, the while loop returns, and the function returns, and the actor shuts down. All right? But we also need to talk to the actor somehow. And to do that, I like to define something I call a handle. And so this is the handle to the actor. And so the idea is that you have a sender for the message passing channel, and we also have a constructor here. So you create a channel, you construct the actor, and then you use the Tokio spawn function to put the run function on a background task. That's what we talked about earlier. It has to run on a background task. Now, you may know that I'm using an MPSC channel for the actor. MPSC, that means multi-producer, single consumer. And so this is what allows us to have multiple senders. We will see a little bit more about that, but yeah, that's why we use this kind of channel. We only need one receiver because, I mean, there's only one actor. Yeah, and this is the send function. Once you have the handle, you can define a send function. If you have multiple message types, you would probably define multiple functions such that the user doesn't have to worry about this enum type. Okay, so now we've seen an example of what an actor could look like. So there are some things in this example where I have very intentionally done it in some specific way. There are also some things where I had to pick one way to do it, and if you're gonna write your own actor, there's no big reason to do it my way or to do it some other way. So let me be explicit about which things are which, and so we will start by talking about the things that I did very intentionally in one way and not some other way. The first thing is that we have two structs instead of just one. If you were writing something like this in a garbage collected language like Java, I think most people would probably just define an actor class, put all of the stuff, the IO resource and so on, as fields, and then the run function, the send function, all of it would be in the same class. But this doesn't work in Rust. And this is really the source of why I think actors are an interesting example for talking about ownership in Rust. So the idea is Rust enforces the single ownership principle. Everything should be owned in one place. And so in the case of actors, you have to make it very clear to the compiler which things are owned by the background task and which things are owned by whoever talks to the background task. So, the best way to do this is to split it into two structs, like this. Because since the actor struct only exists in the background task, there's no way to accidentally access it from the send function, which is outside of the run function, right? Like in Java, you could totally just in the send function, just access the IO resource if you did what I talked about earlier. In Rust, the syntax we're using makes this impossible, and that's what makes the compiler happy. Now, I told you that we wanted to have shared access. The way we do this is that the handle, I have copied it here, it has a derived clone, and that's this thing I talked about, MPSC. We have multiple producers, and the way you get multiple producers is by cloning the sender. That gives you a new sender that goes to the same receiver. And so, if you clone the handle, you get 2 of them. And so the idea is, well, if you take these 2 handles and put them in different places, well, they talk to the same receiver, so now you have shared access. And so you just clone it for everything that needs to access it. That's the idea. Another point I want to make is, in my example, the run function is a standalone function, as opposed to being something in a run block, in an impl block. It's not that you couldn't do this, but I find that people find this less confusing. Now, let me explain why. So let me show you how this code would look if it wasn't an impl block. It would look like this. The thing to notice here is there's no ampersand on self. The reason we need to not have the ampersand is because, well, ownership. We need the run function to own the actor. That's what we talked about before. But the way we do that is to not put an ampersand. And I just find that many people have not seen self without an ampersand before, and so I just find that writing it as a standalone function tends to confuse people less, and that's really the reason I do it this way. It's not just, this works fine if you want to do it, but I find it's less confusing for readers to do the other way. Okay? Now, this is supposed to also be a lesson about ownership. So I'm going to talk a bit about lifetime annotations on your actor types. And my point is, if you put a lifetime annotation on your actor types, you've probably made a mistake. So let's talk about why. So what does this mean? It means that the message type has a pointer to some reference data, but it's stored, the actual owner of the string data is somewhere outside of the message. Of course, this means that the message must not stay alive when the owner is destroyed. The message must be destroyed first. Because if not, then you have a pointer to something that's destroyed. And avoiding that, that's like the entire reason we're using Rust. So let's not do that. Okay? So, maybe you object. We have this one-shot channel, so actually, by waiting on that, we know when the actor is done using the message. And I could say all sorts of stuff, oh, this doesn't work because of cancellation. But there's a more fundamental reason that using lifetimes to accomplish this doesn't work. And that's the fact that if you have a lifetime on the message, then it leaks to the actor like this. Defining the actor struct is required to put a lifetime on it if it's on the message. Maybe you could do something like what I talked about, reasoning with the one-shot channel with unsafe code and raw pointers, but that's where the stuff about cancellation comes in. But when you use normal references and lifetimes, what I'm talking about now is why that doesn't work. So to explain why this breaks, let's first clear up where does the lifetime go. So the first thing to say is that the lifetime goes on the thing that is borrowing from something else. The owner doesn't have the lifetime. Okay? So when you see a type with a lifetime, like this one, that means it's the thing that borrows. Okay. Now, let's talk a bit about how the compiler makes sure that stuff with lifetimes is safe. So I've drawn this diagram. Now, the outermost circle here, that's the duration of the borrow of the owner. And this is basically a region of code that starts when you create the reference to the owner, and it ends whenever you do some sort of incompatible thing on the owner. This could be a move, destroying it. It could also be modifying it. So that's the outer region. Let's talk about the inner region. That's the region in which our value containing the reference lives in. So the thing with the lifetime is the thing with the reference, of course. So if we just disregard the inner circle, then what we want is that the thing with the reference exists only in the region where the owner is borrowed. That ensures that this is safe. The way that the compiler checks this is that when you create the reference is assigned some lifetime, and that lifetime knows when the borrow ends. Furthermore, this lifetime is part of the type system. And so anything that has this reference gets annotated with the same lifetime. And so the idea is that the compiler knows some region, like the lifetime corresponds to some region, and the compiler knows what the region is, and then it checks two things separately. The one thing it checks is that the value with the reference never leaves the lifetime. And interestingly, the value could be destroyed before the lifetime ends. So it just has to never leave it. So it's less than or equal. It's not equal. On the other hand, it checks that the lifetime is less than or equal to the borrow. And this might be less than, because in some cases you can say these two lifetimes must be equal, and then maybe you have two different borrows, and then it picks some region that's smaller than both of them. That's why it's not necessarily equal. So that's how it works. But let's go back to the example. We have our actor, and since it is annotated with a lifetime, because of this, the compiler reasons that there must be, the lifetime is some region of code, and there must be some string somewhere that is associated with this lifetime, and the actor must be destroyed before the string's borrow is done. For simplicity, let's just say the actor must be destroyed before the string is destroyed. The actor can never leave the region in which the string exists. This is enough to explain why this goes wrong. Because, let's think about what this means. The lifetime, that's the reference on the message. And messages to an actor are supposed to be some sort of short-lived object you send to the actor. You send lots of messages over the lifetime of the actor. So the messages are supposed to live for a much shorter duration than the actor. But by putting the lifetime on the actor, you've told the compiler that I want you to make sure that the messages stay alive until after the actor is destroyed, which is the opposite of what we want. It essentially means that you must leak the messages to send them. That's essentially what it means. Otherwise, you can't really get them to live for long enough. So that's the idea. Now that we're talking about lifetimes, let me make another point that I also think is good to talk about. So if you mess this up and put a lifetime on your message, you're probably going to get the error on the call to spawn. And the reason is that Spawn requires that the future is static. And I find that lots of people do not know what this means. Let me first explain what it does not mean. It doesn't mean that the future lives forever. I mean, that would be a memory leak. This does not mean that you have a memory leak. What it means is that the future has no lifetime annotations shorter than static. That's all it means. So for example, if you don't have any lifetime annotations at all, then you certainly don't have any that are shorter than static, and so the compiler is happy. So if we look at the run function, we note that I told you not to put any lifetimes, so there are no lifetimes here. And so there are certainly no lifetimes that are shorter than static. And so the compiler will be happy with your spawn call. That's basically what it means. Okay, now we talked about some things in my example that are important. I also have some details that are not important that I want to explicitly tell you are not important. Because I sometimes get questions, did you do that intentionally or not? And I'm just going to tell you now that the answer is no. The first one is the location of function boundaries. And by that, let me explain. So here we have the handle message function. This is a function boundary. We're calling a function. And if you want to, you could remove the function boundary like this. Just put the function in. This is fine. Do it if you want to. As another example, we could take the message-specific stuff and put it inside a function like this. This is also fine. This pattern can actually be useful if you have many message types, because then you can define a different function for every message type. And so the functions don't have to contain this match with all of this indentation. They can focus just on one message type. So this can be quite useful. Of course, you could put both function boundaries and put the match inside a function too, like this. So yeah, and maybe you think that that's obvious that this is not important. But I mean, I had reasons to make the run function stand alone. So maybe I had reasons to do this too, but for this specific case, I don't. The other thing, so I was talking about how, oh, you should split your stuff into structs. But really what I mean is that you should make sure that it's clear to the compiler which values are on the background task and which are not. One way to do this is to use a struct, like I did. But if you take the fields and just make them arguments or local variables to the function, like you see in this example, this works just as well. Yeah. The point is really that when you make it a local variable or an argument, it is still clear to the compiler that nobody else is going to touch this TCP stream while you're using it. There's no way for anybody else to do that. I mean, it's a local variable. And so the compiler is also happy with this. Yeah. So really my point is, don't use one struct. Two structs or this is fine. Whether or not you should do this or have two structs probably depends on how complicated your actor is. We can make the same point about the messages. I mean, here it's an enum. That's because I wanted to show you that you can have many types of commands by using an enum. But if you wrote this code, you should probably be using this as your message, or even just a tuple. Oh, yeah. I mean, maybe you're only sending the string. In that case, your message type should probably just be a string. So in your real code, there's no reason that you have to put these things in enums or structs unless it makes the code clearer. To make this point clear that you don't need to wrap these things if you don't want to. If it makes the code clear, then you don't have to wrap it. I have a very simple example of an actor. Here you go. So this, according to my definition, this is a complete actor. Let me explain what this means. So sync is a trait from the futures crate. It's an object you can write stuff to. For example, the WebSocket types often implement the sync trait. The forward function also comes from the futures crate. It basically takes a stream and a sync and it implements a run function for us. And so you actually often see this kind of spawn function in the WebSocket examples. And yeah, so I think that this example illustrates that you can go full-blown, lots of struct, lots of boilerplate if you have a super complicated actor. But if you don't, you can do something like this, and you don't have to add that much boilerplate. All right, so I also have some tips and tricks and warnings and that kind of stuff to talk about. So perhaps this part is more interesting if you already know how to write actors. But let's start on a simple one. The first is the idea that you don't actually have to respond. This is what I was talking about in the beginning, that you can do this. And this is the example where the outside influence that started the operation, it doesn't have to wait around. It can send the message, go off, do something else, and then we can handle the message later. That's how you do it. The send function becomes much simpler if you do this. This is not something I want to go into a lot of detail in, but I just want to say you can also have timers. I mean, this is the thing I mentioned earlier too, that actors can do stuff on their own, for example, with timers. And this example just shows the basics of how you do that. If you ever want to have multiple event sources, such as a channel and a timer, or maybe 2 channels, then the tool to go for is called Tokio Select. You can go look up at the documentation to see how to use it in the specific case. That could be an entire talk, I guess, but I just wanted to tell you that if you want to do that, go look for select. Now there's an interesting point here. I mean, my actor example used Tokyo spawn to put it on a background task. But maybe your actor is working with some blocking I/O resource. Maybe it's a diesel database connection. In that case, you cannot put it on a background task using Tokyo spawn. You have to spawn an actual dedicated thread. And here there's an interesting point to make, which is that you should actually be using the STD, standard library spawn function, as opposed to the Tokyo spawn blocking function, if you do this. And the reason is that spawn blocking puts your actor on a thread pool with a limit. And so if you put a bunch of actors that just sleep indefinitely on a channel, you're going to exhaust the limit, and then nobody else wants to use spawn blocking. Like, that will just not work anymore because you hit the limit. So spawn blocking is really supposed to be tasks that will exit on their own eventually to avoid this kind of, I mean, this could really be a deadlock if you have actors that wait on spawning an actor, for example. So yeah, that's a little point of warning. Now, there's also another thing that you have to think about when using actors, which is that you have to think about what should happen if the actor cannot keep up with how quickly you're sending messages. Now, there are several ways to do it. The first one is back pressure. Back pressure is very nice, and it is what happens when you use a bounded channel and use the send function that you need to await. That's what we've done in our example so far. So what happens when you do this is just that if you cannot send a message, then the send function will sleep until you can send a message. And this prevents whoever is creating messages from creating more messages. And so, if the actor can't keep up, well, we just stop producing messages. And that's perhaps the nicest way to handle it. But maybe you don't have any control over how fast messages are incoming. Maybe you are a web server, people are sending you connections super quickly, and maybe you just want to respond to some of them with an error if you can't keep up. There are two variants of this. It's called load shedding. The first one is to just drop some of the messages. For example, maybe you only care about the newest messages, and if there's a super old message, then maybe just throw it away. For example, the Tokio broadcast channel, it does exactly this. If you call send and there's no more space, well, it just deletes the oldest message and puts the new one in, and the receiver will get told that, oh, I missed this many messages because you were too slow. The other one is to kill the actor, which is the way to do this is to use a bounded channel and to use the try send function. This function will try to send, and if there's no space, instead of sleeping, it will just give you an error. Now, I told you that there are 3 things you can do, but there's actually a 4th one. This is what happens when you use an unbounded channel. In this case, well, if the actor can't keep up, well, the number of messages in the channel just keeps increasing until you run out of memory. Unbounded channels are very convenient, but there are usually a memory leak waiting to happen. So, use at your own risk. Okay. Here's another point and a warning. So, if you have many actors, they can talk to each other. You can just put the actor handle of one actor in another one. This diagram shows some sort of chat room where maybe you have an actor for the chat room and an actor for each connection, and they talk to each other and so on. But here, you actually have to be careful. Because you have a cycle where messages go here and then they go back. And if both of these messages in the cycle use back pressure, then that's probably going to deadlock. Because what ends up happening is that actor 1 tries to send a message, but it can't because there's no space, and so it goes to sleep. But then actor 2 also tries to send a message back, but it can't because there's no space, and so it goes to sleep. But for either of them to wake up, the other one has to read a message, which doesn't happen because it's waiting for space. The way to fix this is to, well, for one, if you don't have cycles, then you don't have this problem. But furthermore, if you do have cycles, well, if you just make sure not to use back pressure, then it's also okay. For example, this is the strategy where you kill the actor if there's no space. Try send. And in this case, there's no way to deadlock because the chat room can never get stuck on sending a message. It always finishes immediately, whether it's an error or not. And so you avoid the deadlock. So you can break the cycle, I call it. Of course, this also applies to longer cycles. As whenever you have a cycle, you must break it somewhere using a channel where the send function does not sleep. You could use unbounded, well, that's a memory leak, but okay. Or you could use try send on a bounded channel, one-shot channels, broadcast channels. All of these are okay. They don't use back pressure. All right. Now, dynamic dispatch. So this is actually my favorite point. So dynamic dispatch, that's when you have multiple types that something might be, but you don't know which one until runtime. And so you dynamically figure out which kind of methods to call on the type. Normally, doing this requires the use of dyn trait. That could be dyn async read, or dyn async write, or dyn stream, or whatever, dyn future, but it requires some sort of dyn trait to do this. However, if you are using actors, then you don't need to use dyn trait, because actors provide dynamic dispatch on their own. Let's see why. So, here's an actor. Well, the I/O resource, it's something that you can read and write to. And then there's a receiver. Well, how does the handle look? It looks like this. And the interesting thing to note is that the generic does not leak to the handle. And that's why it works. So for example, just to see how this happens, many database servers allow both remote connections over TCP streams or local connections over Unix streams. So if you do this, then you can just use a handle to do this without having any sort of special handling for it, and the code that has the handle doesn't have to care. Okay. So now I'm actually done. Yeah, that's it. Are there any questions?
So you were mentioning that your actors keep endos to other actors, and those actors can be killed. So how do you deal? What's your strategy for dealing with when they die and other actors need to know that some other actors are keeping their place? So do you have some kind of like central registry, or do you keep updating endos around, or what do you do? Thank you.
Well, it sounds like your question is, I talked about in the beginning how, say, Erlang has some sort of opinions about how error handling should be done when you work with actors. If you do actors the way I did it, you essentially have to do it on your own. So if you want to restart the actor yourself, then you're going to have to write some code that restarts it. So yeah, and maybe I should mention that the way you actually kill an actor is, well, of course you could send a message telling it to shut down, but one way to do it is to store the join handle that you got when you called spawn. This has a function to kill it, an abort call. So yeah.
Hi, what a great talk. One of the things that the Java example where it's all in one object that you described, one of the appeals to me is that when I don't know what's going on, I have access to that object in a kind of diagnostic way, and I could like go introspect it and see what's going on and figure out things that are going wrong. And I'm wondering, how do I do that when I've spawned it off, and essentially, in some sense, this actor object has just gone off into the, into a black hole somewhere, inaccessible to, my debug code. How would you handle that?
I mean, the point of the spawning it off is to make it inaccessible. One way is there's this crate called tracing that will let you output information from all sorts of places and collect it somewhere. Or you could write something in the actor itself, but you essentially have to do something like that. Put something in the actor, maybe using tracing, which will output this debugging information somewhere.
Thank you, Alice. And let's hypothesize I have a really bad idea related to the allocation of the message. I don't like to allocate a string or maybe something bigger for my messages. And the bad idea is, okay, I can use an arena on top of all the structure of my actor, and I can abstract the actor related to the allocator. Okay, this makes all the lifetime pervasives, and it creates a lot of mess. Okay, it could be worth, or you can just say, okay, just use gmalloc. It's better for that purpose, and it's okay. Or maybe it could be worth to create some kind of allocation-based actor. Thank you.
Yeah, so one of the advantages of the argmutex approach that I talked about in the beginning is that when you use a mutex, you don't have to make these allocations. So if you don't need these fancy features with background operations and so on, then using a mutex would be one way to avoid these allocations. When you are sending stuff over channels, like you do with actors, that essentially requires you to allocate. I mean, maybe you could do something clever where you make space in the message type for your string if you know that it's short always. But you are not going to avoid all allocations when using actors. That's one of the downsides of them.
Thanks. So you mentioned one of the a bunch of solutions for when you have lots of when you can't keep up with the messages you're being sent. One thing I was also thinking of is the possibility of multiple actors working on the same message type. Is there any particular downside to something like that? I mean, you would need to at least have a way of distributing those tasks. So that's one part of it, but are there any other issues there? Thank you.
Yeah, I mean, what you could do is, for example, the async channel crate provides channels that let you have multiple receivers and multiple senders where each message goes to only one receiver. And so if you used that, then you could spawn multiple background tasks and handle them like this. And then you could hope that Tokio's work stealing will distribute these on different threads such that they can be handled in parallel. Or maybe the bottleneck is the IO resource. So maybe you could open multiple connections and that makes it faster. So in that case, the work stealing doesn't even necessarily have to happen. So yeah, it could be done.
Okay, so if there are not any more questions, I'd like to thank you again, Alice, for the talk.